Alright, what we're going to work on in this video is a particular type of problem known as Hess's Law. And before we get to the problem that's on the screen, I want to come over here and remind you of a couple of things that we've seen in the previous videos. One of the things that we've seen is that heat is equal to the enthalpy change. Enthalpy change is equal to the heat as long as you're at constant pressure. And for us in general chemistry, we're at constant pressure. And this enthalpy change, or the heat, both, are proportional to the mass. Remember that we had, this is my proportional sign, Q equals ms delta T. That M was the mass. So the amount of heat released is proportional to the mass. It's also proportional to the moles. It is simply proportional to the amount. In the previous video, we said that if we took the coefficients of everybody in our reaction and we halved them, we put them in half, then our delta H, our enthalpy change for that reaction with half the coefficients, was actually half the amount. We also learned early on that the Q of a forward process was equal to the negative Q of the reverse process. We see that in our calorimetry problems. If you lose heat from something in your calorimeter, it is absorbed by the other thing in your calorimeter. So a forward process and a reverse process have exactly the same numerical value of heat, but one of them is releasing the heat, the other is absorbing the heat. We also saw that in our last video. As we look at a chemical reaction, if you turn the reaction around, then the heat goes on the other side of the arrow, the other side of the thermochemical equation. If you start with an exothermic reaction that is releasing heat, and you turn the reaction around and write it in the backwards direction, it's now an endothermic reaction. It is absorbing that exact amount of heat. So what we want to do, now come over here and look at this problem, we want to use a couple of reactions, these two, that for whatever reason we are able to get delta H values. We'll call this reaction 1 and this is reaction 2. So we are able to get enthalpy values, thermochemical equations. We find the delta H's for these two reactions as written. This is my delta H for reaction 1, this is my delta H for reaction 2. And I want to use them to find the delta H for this reaction listed up here in the problem that I don't know the delta H for. All right, the way that this is going to be formulated for you at this level is we're looking for the delta H of this reaction. I will give you reactions that can be used to find the delta H for this reaction. If this were a real world scenario, you'd have to figure out, well, what reactions do I need in order to get the delta H of the one that I'm looking for. In our scenario, I'll give you the reactions that you need to find that delta H. But here's how you're going to do that. This is kind of like a matching game or a puzzle. I need to manipulate these two reactions so that when I add these two reactions together, they give me this reaction up here that I'm looking for. Because, and we saw this earlier as well, if I have a series of steps with energy changes, I can add all those steps together to give me an overall energy change. The delta H of a total process, of an overall process, is equal to the sum of the delta H's of the steps of the process. If I add up all the steps in a total process, I'll get an overall delta H. This comes directly from the fact that the enthalpy change is a state function. Since it's a state function, delta H equals the final minus the initial, which means that it doesn't matter how many steps I have in the process, I can simply add up all those steps. So here we go. What I'm trying to do is I'm trying to match. For example, I'm trying to match the W, the tungsten, that I desire with the reactions that are given down here. Now there are some stipulations on how I'm going to match this. First of all, I find it down here. There it is. If the tungsten showed up in both reactions, I would skip it and move on to something else. I don't want to try to match something that shows up in more than one reaction. And you'll come across these in your practice. But this tungsten only shows up in one place. It shows up in reaction 1. To match it, I want it on the same side of the arrow, and I want its coefficient the same. So to get equation 1 to match the equation that I'm looking for, I need the coefficient to only be 1. It's on the correct side of the arrow. It is a reactant in equation 1. It's a reactant in the equation I'm trying to match it to. But I only want 1 tungsten. And so I will rewrite equation 1 with only 1 tungsten, which means now I have 3/2 oxygen gas and 1 WO3 solid. Sometimes I won't, when I'm working these problems out and doing my work, I'll leave these states off. I won't write the states. As long as I see that they do match the reaction I'm trying to find, I'll go ahead and leave them off just so that my workspace isn't so cluttered. All right, now I'm going to rewrite the delta H for this reaction 1. It's no longer negative 1685.4. Now this reaction is half of what it used to be. I divide out all the coefficients by 2, and so the delta H for this reaction is half of what it used to be, or 842.7. Now it's still negative because that amount of energy is being released, but it is half of what it was because I took all the coefficients and divided by 2. All right, next, my next step in trying to figure out what the delta H is for this top reaction is I need to match something else. So I might move on to the H2O and try to match it. And again, what I might find is that H2O shows up in this first reaction that I've already manipulated. In that case, I'm going to skip it and move on to something else. I'm looking for something to match that shows up in a reaction I have not manipulated yet. And in this case, water does show up in this second reaction, and I haven't manipulated it yet, so let's manipulate it. What do I need to do to reaction number 2 to make the water match what I'm trying to find? This top reaction is what I'm trying to find. One thing that's wrong is my coefficient is wrong. I need a coefficient of 3. It's only got a coefficient of 1. Another thing that's wrong is that it's on the wrong side of the arrow. My water in the reaction I'm trying to find is in the reactants. The water in this second equation is in the products. So I need to reverse reaction 2. I need to flip it around, and I need to multiply it by 3. I didn't write it up here. I probably should have. I multiplied reaction 1 by 1/2, or I divided by 2 to get this equation with only 1 W. Sorry about that. I forgot to write that. So I am reversing equation 2 and multiplying by 3. So let me do that. That means I have 3 H2O gas. I'm going to have 3 H2 on this side because I am reversing it, and I'll have 3/2 oxygen. So I reversed the reaction and I multiplied it by 3, and the whole reason was to make it match the water in the reaction up above. So I've done this to both reactions. I've manipulated both reactions to make them match the reaction that I'm trying to find in the question. Again, what happened is this delta H is now different. The delta H of this new reaction 2 that I've manipulated, I reversed it, so it's no longer going to be negative, it's going to be positive. And I multiplied it by 3, so I will need to multiply that numerical value by 3, in which case my new delta H2 is 725.454 kilojoules. It is a positive numerical value now. Now the last step is to say these are the 2 steps that should give me the reaction that I'm trying to find. Let's prove it. Let's add these 2 reactions together. Remember the arrow, when we're adding reactions together, the arrow is kind of like the equal sign. Everything that's on the left stays on the left. Everything that's on the right stays on the right. So I end up with, oh, and by the way, you might find that some things cancel. You want to go ahead and cancel them. These are kind of like our spectator ions in our precipitation reactions. I see that I have 3/2 oxygen on both sides, so the 3/2 oxygens will cancel. So I'm left with W, tungsten, solid, plus 3 H2O gas. I added my things for my left. WO3, solid, plus 3H2 gas on the right. I added my products without adding the oxygen. And you'll notice, yay, it is exactly the reaction that we're looking for. If it's not the reaction you're looking for at this point, you have done something wrong. Try again. The delta H then for this overall reaction is the sum of the delta H's of the steps. So essentially I take my negative 842.7 kilojoules and I add my positive 725.454 kilojoules, and I find that the delta H overall for my new reaction is negative 117.246 kilojoules. So I have found the delta H for a reaction that I was not able to do in the laboratory by using a couple of reactions that I did know delta H is for. This process is called Hess's Law.